Hi, everyone. Thank you for staying this late. I know it's the last day of the conference. And I'm going to check if I can keep moving these. Okay. So my name's Ali Imami. I am a rising fourth year graduate student at the University of Toledo. My PhD is in bioinformatics, and I work in the Cognitive Disorders Research Lab. To yeah, that's not.
That's over here.
Yeah, it's just
Very difficult with this computer.
okay. Perfect. So that works. So in the interest of disclosures, I have nothing to disclose. And just so we're all on the same page, what do I mean when I talk about the kinome? When I say kinome, I don't really mean every kinase ever. I mean the specific protein kinases that are active in a given condition in a given time point. And that's the active kinome, and that's what I refer to when I say kinome. And what are kinases? That those are enzymes that have exactly one job. They take a phosphate and stick it to something that can accept a phosphate. The kinome analysis is generally done on a single kinase basis, but there have been improvements, there have been advances in the area. And then one of the high throughput kinase kinome analysis is the PAM station 12. The PAM station 12 is a microarray which has two flavors of chips, the protein tyrosine kinase activity chip and the serine threonine kinase activity chip. The PAM station can contain 3 chips. Each chip has 4 wells. Each well has a variable number of spots. Each spot has peptides. And when you add your cell lysate or recombinant kinase and ATP onto that, phosphorylates things. You add a reactive antibody, it glows up. You take pictures, it tells you how much the activity is. This is sort of our lab's bread and butter. This is something we do on a completely regular basis. This is standard workflow, and I tend to do the last 2 parts. This is a sample of one figure that we generate in a report that usually goes anywhere between 40 and 60 pages, and it's all dynamically generated. These are 4 more methods. The cursor, the one on the top right, is something that our lab developed, and then we have other ways that we have automated all of that stuff, generate reports that make sense, but it's still run by me. And this is one of each report examples. This is another consensus report. So I hope you're beginning to see how much work that is, if every experiment being a unique experiment, and it just adds up. The biological sample prep is something I don't do, thank God. I mean, that would ruin the experiments, but everything else from image analysis to contextual interpretation, I'm usually the person doing it or the person who is working with our collaborators, making sure that it's done correctly. And this, I'm in my 4th year. This has been taking an unreasonable amount of my time. And at this point, I'm thinking, there's no way I can write my dissertation if I keep doing this. And at that point, my advisor comes in and I was like, yeah, we have 4 more collaborators that need to run about 5 more experiments. So I thought something had to be done. And the solution that I came up with is KADL. I like to call it KADL, the Kinome Analysis Description Language. The goal here is to make it easy for people who are non-experts to describe the end result. If any one of you has ever worked with SQL or SQL, it's a declarative language, just describes what do you want to do, and everything happens within SQL's engine. Think of it something like that. People describe the analysis and the output they want. They give it to something that can understand that, parse that, and give them the exact result. That takes out everything from my workflow, from biological sample preparations, all the way up to contextual interpretation. So I can then help with contextual interpretation, but the middle part, I don't have to do every time. This is the ideal example of what this should look like. On the left side, you have a lab scientist. A bench scientist has a beaker. I don't know why it's bubbling. I would probably stay away from it. In the middle, you have a KADL script. This is the minimum KADL script that you can have. And on the right side, there's a computer. Again, I think it's an all-in-one computer, but I would not be able to operate it without a keyboard and a mouse. But that's what BioRender had. These are the language constructs, the building blocks that were built on top of. You have simple enumerations. The KADL specification decides what features are available and how it's going to be parsed. You can have a single string. There are multiple things, but an analysis target or analysis name will just create a new directory, make it easy for people to keep track of their experiments. There's a simple list, space separated, that allows you to define groups. There are 12 wells in a single run for a PAM station. So you can have anywhere between 1 and 12 groups. More often it's between 2 and 4. So you see there are 4 groups: wild type, knockout, overexpression, and heat inactivated. And then you can also have more complex lists. These are supposed to be just built out of the groups that are defined, and the mapping that happens automatically. Then there are Boolean switches, and pretty much all of the rest of it is these Boolean switches. If it's there, we generate that or do it that way. If it's not there, it doesn't happen. There's a switch there that says heat map, which generates the heat map that you saw earlier. If it doesn't say heat map, we don't generate a heat map. So it is, so this is the internal structure of that. You have the chip, which has generated the data. You have the script. It's put in a single directory. Somebody drops it onto our binary, and that binary then runs. That binary is implemented in Rust, which makes it, as the common wisdom holds, blazingly fast. The Rust binary also has templated R scripts embedded inside it. So all the data that it gets from our KADL script, it just templates that into that, and then it runs it ad hoc with whatever R engine is available. And you have that loop, and it keeps on running until you get to the end. And then you're done. So ideally, if you're a bench scientist or not the most computationally interested person, you can get that data. You can do this at around noon, let your computer run, go grab lunch. By the time you're back, this is done. The current status of this is that we have the KADL spec finalized. That's available on our GitHub. It's on the Cognis Res Lab, because they would not let me put the whole name on it. It's too long. The spec is now version 1.0. Anybody wants to re-implement it in C, please be my guest. The interpreter that I've been working on in Rust that works with R4 is currently still beta, but it's 0.8.1. I can run it with minimal errors, and I've not really run into any major issues so far, and I've run about a dozen reports through that. The project, the source code's open source under MIT and Apache 2 licenses, available on GitHub. Binaries precompiled for most architectures, also available on GitHub. The Rust system, which uses R as a bridge, is also available as a library on crates.io, which is Rust's extension distribution system. And if you just want it to run, which is what I would recommend, it's also available on Docker Hub in batteries included container. You just run it, Docker run, load this file, run it. To the end, I would like to acknowledge my advisor, Dr. Robert Smith, Smita, Belly, Ryan, my colleagues, everybody else at the Cognitive Disorders Research Lab. On the right side, you see my family. From left to right, it's myself, my younger daughter, my wife, and my older daughter. So they are my biggest source of support. The University of Toledo and the Fulbright Commission for making sure I am here in front of you. Thank you. Any questions I'll take? Yes.
Great talk. So I'm curious whether this descriptive language was made for like a particular platform that does like kind of analysis, or like it can like run given the data of a particular format.
So the format doesn't matter for this. And ideally, I keep describing it as for high throughput kinome analysis, PAM chip's not the only way. You have KinoBeats, you have Kinative, you also have mass spectrometry, you have the P100 chip. There's multiple ways to do that. And I'd be happy as we grow, maybe by the time we get to a KADL 2.0 spec, like 1.1 we're already working on. So as we keep extending it, we can keep including more and more stuff that's just built on top of, as long as we can analyze it in R and Python, we can work with it.